This is part 2 of the lab determining the mass of a large granite sphere in an interactive sculpture. In the first section, in the first episode, we did chapters 1 and 2 and skipped to 5. In this section, we'll do the integration of to determine the motion of inertia of a sphere using some calculus in chapter 3, and if we have time, to squeeze in chapter 4. These two chapters are going to be at maybe an AP calculus level, college calculus level, college physics level. So I'll jump right to there. And continuing to chapters 3 and 4 for the moment of inertia calculations. Here are just a few of many equations for a moment of inertia in your physics textbook or calculus textbook. Maybe you have these. And the one we're going to be finding is a solid sphere. I is equal to 2/5 mr squared. Integrating to determine the moment of inertia of a solid sphere of uniform density. Because, at least in my classes, we often use the moment of inertia of a disk, I'm going to integrate using a disk method. And then in chapter 4, I'll show you how to find the moment of inertia of a disk by integrating. This is not the easiest and most direct route, but because we have to use both moment of inertias, I want to show where they both come from. So I'll use one to find the other and then find the disk one in chapter 4. The moment of inertia of a solid sphere can also be done, and is usually done, by integrating using a lot of tiny hollow shells or spheres called the shell method. So let's go ahead and continue with my disk method here. With the disk method, the sphere can be thought of as composed of a very large number of very thin disks stacked, here's a disk, from -r on up to r. Each disk would have a moment of inertia of I equals 1/2 mr squared, which is right here. We'll be using that for now. So for now, that falls out of the sky or is determined there experimentally, but I'll show you in chapter 4 how we can actually derive that using calculus. Or I should say, obtain that using calculus. An object like this one, that is rotating around an axis this way, has a moment of inertia that can be determined experimentally. It is I equals mr squared. We will consider a tiny fragment with a tiny mass rotating about the axis to have a moment of inertia of I equals dm times r squared for a tiny piece. Notice my coordinates. Unusual. X is into and out of the board, y is right and left, z is up and down. Here are my same coordinates again. These are a little unusual. X is in and out of the board, y is left and right, z is up and down. Using that coordinate system, for a thin disk, we will set up the equation I is equal to the integral of 1/2 y squared dm, where dz is the thickness, y is left and right this time. Well, y is playing the role of radius. That's important to realize. But we can't use dm because it doesn't match with this y. This dm doesn't match with this y. So we've got to do some work. We can use dz if dz helps us find the volume of the disk based on its distance. It's not a direct route, but we can get there. This does work for a solid sphere of uniform density like the one we have because mass and volume are directly proportional in the density equation. Since density equals mass divided by volume, we can get by with that substitution, I guess. Okay, the volume of our sphere is 4 thirds times pi r cubed. Now, I'm not going to show you how to do that today. You can do that one on your own, but that's an exercise that needs done too. Since mass and volume are in direct proportion because of this density equation, we can set up a ratio to determine the equivalent of dm. So if we take the mass over volume for the whole sphere, that should be equal to the mass of a very thin disk divided by the volume of a very thin disk, since it's the density of the same material. That should be proportional. So if we rearrange this equality, by moving this up here, then that's what we get. And if we rearrange this to organize it a little more, we get dm equals 3m y squared dz over 4r cubed. And let's take that to the next page. And here it is right here. We're going to end up substituting this in. Now going back here, let's go back to our original equation, y equals 1/2, or the integral of 1/2 y squared dm. Here it is. I'm going to put this substitution in for dm because that dm isn't going to get us very far. So I is now the integral of all of this mess. And this is going to get worse and worse before it starts to get better. If we simplify by making these y squares go to become a y4, this is what we get. But we still have yz or zz or r, I, we're kind of limited right now. What we can do is take the constants out. We've got I is equal to the y to the 4th dz. Okay, now at least the integral part is getting a little simpler, but don't worry, it will get worse. Again, we face this same situation. We can't do this integration directly because this y and this dz don't work together. But we can get it. We can get a y in there. We can substitute in for y if we use the equation for the circle made by our stack of thin discs. So we've got y this way, z this way. We're on a circle, so we've got this radius here. So we've got the equation for a circle, basically. Z squared plus y squared equals r squared. If we are rearranged to isolate for y, then we can put this r squared minus z squared in for this y to the 4th. It'd be y squared squared, put this in, and then we've got a big mess. That just keeps getting worse. Okay, now we've got a binomial. So if we go another step and expand this binomial, now we've got everything in terms of z, though. So we do go ahead and perform this integration, taking into account we have dz here, and this is our result. We've got all these constants. I is equal to all these constant times r to the 4th z minus 2r squared z cubed over 3 plus z to the 5th divided by 5. And we're taking that from negative r up to r. And now we can talk about all these little z disks, dz disks, stacked on top of one another. When you go ahead and take into account from negative r to r, this is the whole mess that you get. And from here on, it starts getting better. We can simplify these terms to get this, bring out the r to the 5th, and then we've got this. Now we can put our everything in terms of to the denominator of a common 15. Simplify, we've got 16 15ths, we've got an 8 here, a 16 there, a 3 there, a 15, and that reduces to I equals 2/5 mr squared. And so we now have derived, well, we've integrated to get our moment of inertia of a sphere. Next chapter, integrating to find the moment of inertia of a solid disk. Those little disks that we stacked up. So I'll pause here and work on that one. Back from my pause, I just want to make sure it would fit on this screencast, and it does with plenty of room, and kind of review this a little bit before I started. So we're now trying to find the basically moment of inertia of each one of these little disks that we're stacking up that we said that they fell out of the sky. Okay, so an object rotating around an axis, now I'm in a disk. Okay, I'm looking on this disk as from above. This is no longer a sphere. An object rotating around an axis has a moment of inertia that can be determined experimentally. This was a little block going around and whirling around on a string, for example. Its moment of inertia would be I is equal to mr squared. We'll consider a tiny fragment, dm, with a tiny mass rotating about the axis to have a moment of inertia of di is equal to dm times r squared, or di is equal to r squared times dm. So the inertia of the disk is the integral from r equals 0 to r equals r, and that would be from the center of this little radius all the way out to the big edge r. Applying that integral to r squared dm. But we have a problem. This r and this dm are not in agreement, so we've got to get there first, maybe by some substitutions. Once again, we're going to pull the same trick we did before. We're going to take advantage of the fact that in the density equation, mass and volume are proportional. Density equals mass divided by volume. As this tiny fragment rotates around the center, it circumscribes a hoop with the width dr that has a mass of dm. Now this little whirling fragment is going to make a hoop. Similar to what we did in Chapter 3, we're going to set up a proportionality using the tiny fragment's mass and volume over the whole disk's mass and volume. So the fragment's mass as compared to the whole mass, dm over m, is a proportionality equal to 2 times pi times r, that's the circumference, times the thickness, divided by pi times r squared, the disk area. And if you bring m up here, you end up with 2mr dr divided by r squared. Looks like murder. There it is in blue. Okay, so we're going to save that. We're going to use it for later. Now, back to the idea of this fragment moving around, or an object moving around. I equals mr squared, or I is equal to r squared times n. So di, for a tiny fragment, is equal to the integral of r squared times dm. I is then equal to the integral from r squared of r squared times, and let's substitute all this in for dm now. Okay, and here we have it up here. We can bring the 2 and the m and the big R squared out because they're fixed. And we're doing that integral from 0 to the outside edge r of r cubed dr. Now we can do that. That was a fairly elementary or introductory maybe integration. So that part is r to the 4th over r, taking that from 0 to big R, the outside radius. When you plug that in, and this is what you get. 2 times m times r to the 4th over r squared, and also over the 4th, and it simplifies to mr squared over 2, or 1/2 mr squared. It looks like we've got everything squared away.